Here, we're going to look at multiple regression, and specifically, we're going to look to see if the different predictors are significant. Now, in previous video, we looked at how to do multiple regression, how to get this equation of that predicts something, given a few predictors. And here we're going to test to see if the predictors actually are significant. Can we be sure that they're positive or negative, or should we do better to ignore them? Now let's go back to the example that we followed in a previous video, and the link to this video is in the description box if you haven't seen it. And we have data from salaries at a lumber company, and we predicted the salaries from education, age, and sex. And we came up with an equation. But what we want to do now that we've studied significance testing, is we want to ask, are all the predictors significant, or are there some that we can't trust? What does it actually mean, the significant? The significant means here that we can be reasonably sure that the predictor in the population, if we were to look at everyone's scores, not just the sample scores, is either positive or negative. So let's look at that example that we had previously. Here it is. Now, what we had was this was a homework assignment that we did, and we have the employee's education, age, and sex, and their income, and we did a regression analysis with these three variables: education, age, and sex. And we saw the output that we got gave an R squared of 44. That means 44% of the variance, or 44% of the variation in yearly earnings, could be accounted for by education, age, and sex. And what we're going to do now that we can do significance testing, is first of all, we can look to see if the entire model is significant, and that's what this significance of F means. And it says 0.000. That's actually, if we add a few decimal places, we'll eventually get some numbers there. We got some numbers there. So this was a very significant model. There's no doubt about it that with accounting for 44% of the variation, it was important that it was significant. But now let's look at the specific predictors. We had education, age, and sex, and let's highlight those three because we want to see if they're significant. And we look at the p-value for the three of them, and we see that they are significant. And so what does that mean? The equation that we got using these coefficients was y equals 44,700 times x1, where x1 was education, minus 18,200 minus x3, where that was sex, where 1 equals male or 2 equals female, and then plus 660 x2, which is your age in years. So that meant that for each additional year in age, the salary increased by $660. For each additional year of education, the salary increased by $4,700, and that males on the average, controlling for education and age, because when we do multiple regression, it removes the overlap between these, and we can say that that's controlling for the other variables. Males on the average earned $18,200 more than females. Now, these p-values tell us that, yes, we can be sure that education adds something to it, that that's what the significant means, that the coefficient is positive. The coefficient for age is also positive because the p-value is less than 0.05. And so we can be sure that education predicts additional salary. And the p-value for sex indicates that, yes, we can be sure that males on the average earn more than females. And so, in a sense, you lose money for being a female, just using these three variables in the predictor. Now, there's a lot of other things that predict what what you earn, like your actual job, how successful you are at your job, how productive you are. This is a lumber company, so there's probably some dangerous, dirty jobs. That's a technical term, dirty job. There are jobs where you get dirty. A lot of people don't want to have those, and so the people that have the dangerous and dirty jobs probably get paid more, and that might account for an awful lot of the differences in the sex pay because you're kind of the stereotype of the lumberjack living out in the forest, cutting down trees. That's you almost always think of a male doing that, and that's probably the case in this study also. So we can be sure of the directions of these coefficients because the p-values are zero. In fact, if we look at the our confidence intervals, we'll see that, okay, the education, you get between 29, 69, and 63, 67 per year. Age, between 300s, 900s. And the loss for being females is between 25,000 and 11,000. We can be sure, given this confidence interval there. So these are all negative, these are always positive, and these are always positive also. So that's another way of saying that we can be sure that these coefficients are significant. All right, let's go back to our text here. And what we're going to do now is we're going to run a regression analysis, and we're going to look at, we're going to look at some class data, and we want to see if we can predict who will like Justin Bieber based on demographics. So let's get the course data that we're using here. And here I have some course data, and I've asked people how much they like Justin Bieber. 1 is not at all, 5 is very much, how much they like the Kardashians, how much they like Star Wars, quality of relationship with their boss, a few other things. But we're interested in their sex, their age, and their shoe size. We want to find out if we can predict who is more likely to like Justin Bieber using these 3 variables, and which of these variables are significant predictors and which ones aren't. So that's what we're going to do here. So we go to Data and Data Analysis, which you should have installed, but you can see the video on how to do it if you don't. We're going to go to Regression. Okay. Now the Y input range is what we're trying to predict. So we're trying to predict how much people like Justin Bieber. And then the X input range are all the variables that we're going to look at. So we're going to look at sex, age, and shoe size. And I'm going to select all the data in the table here. And I have labels because that first row is the label of the variables. And I'm going to put the output in a new worksheet fly. And I'm going to call that predicting liking, that's liking Justin Bieber. So we'll get a new tab down here, and I click OK, and we go to the new tab, and we have this wall of numbers. So let's round to these numbers, home, number, and put it in number format. Let's make the columns wider so that we can read them. And okay, so let's see what we get. First of all, we get the R square of 0.40, and that means 40% of the variation of how much people like Justin Bieber is predicted by these 3 variables. So that's pretty good. And this model is significant, so that is good. If this wasn't significant, then we'd say, oh man, the results we're getting are just like the results we get from chance. So we wouldn't even want to look at the other results, or we'd want to try a different model, maybe with fewer variables. And so we have information on the sex, age, and shoe size. So as sex goes up, which means going from male to female, females like Justin Bieber more. Age liking Justin Bieber goes down, and shoe size, liking Justin Bieber goes down also. People with bigger feet don't like him as much. Now, sex and shoe size would definitely be related, but we're removing the overlap between them. So these contribute things independently. Oh, and so just looking at the coefficient B here, we say, oh, shoe size is the best predictor. But no, we can't do that. What we need to do is we need to see if any of these are actually significant. And to do so, we go over to the p-values here, and we see that, oh, sex isn't a significant predictor of liking Justin Bieber. Well, it's a bit surprising, but that's how it is. Now, shoe size is closer to being a significant predictor of Justin Bieber. And so maybe that's why sex was so far away, is because shoe size includes a lot of information about sex. And maybe it's not significant. So we can't really conclude that it's would be a predictor anyway. But here we have age, and age is significant. P equals 0.01. Add a few decimal points, and it's actually less than 0.01, 0.008. And so the only significant predictor that we have of who likes Justin Bieber is age, and that people that as people get older, they like Justin Bieber more. And so we would leave these other two models out, two variables out of our model, and say that the only significant predictor we have is age. So that's how we test the significance of the different coefficients that we have in multiple regression. Now let's keep talking about how we can some of the meanings of the multiple regression. So let's look here. Now, up to this point, when we've been looking at the results that Excel gives us coefficients, and the APA manual always calls these B, but a lot of times when you read journal articles, standardized coefficients are going to be used instead. And these standardized coefficients are called beta. Now, what does standardized mean? It means like it would basically be the coefficient that we were doing if instead of entering raw scores into the Excel, we entered z-scores into Excel. And so the advantage of using these standardized betas is that they have the same intuitive meaning as R. They almost always go from -1 to +1, and they basically have the same meaning of R. It's an effect size. So you could use it in meta-analyses, for example, and you can use them to compare the strength of the different coefficients if we have beta. If we just compare B's, it depends on what units that we're measuring. If we're measuring things in years or inches or things like that. But when we use beta, we can compare the coefficients to see which one's stronger. Now, for what we can do with regression analysis, we can actually try different models where we enter different variables into the equation to see which one gives us the best equation. Now, you might recall that when we look at Excel, we always get this R squared, and that shows how much variation is accounted for by the model. And so we want a model that has a high R squared, but because of the math of things, no matter how much, whenever you enter a new variable, R squared will always go up a little bit. So we need to look at if the change, well, first of all, we need to look at R squared to see if it's significant. And that's what we did on the Justin Bieber example and the other one. We looked at that overall significance of the model. But when we add new models to it, we want to check the significance, first of all, of the new betas, and also the change of R squared, sometimes called delta R squared, to see if this new model adds anything to our predictions beyond what we would expect by chance. So let's look at an example. And here we have what's known as a hierarchical multiple regression analysis. This is typical of the type of regression analyses that you would see in a journal article, and it provides standardized beta coefficients. And it is trying to predict insomnia from different characteristics of people and their psychological states, their demographic information. And so everything is going to be reported as a predictor of insomnia. So somebody's done a survey of people asking them how much insomnia they have, a bunch of other questions. And we start off with a univariate model. What does univariate mean? Just one variable. So this is giving us the correlation between insomnia and, first of all, sex. Female equals 0, 1 equals male. So that would mean that females have more insomnia than males. Age, insomnia is positively correlated with age. Older people have more insomnia. With education, going from low to high, it's negatively associated with higher education. And these stars indicate that they're all significant. It gives us a p-value according to the number of stars they have. Now, 1 star is p less than 0.10, so that's marginally significant. So it says partnership, living with a partner. That's generally if you're married or not. And so being married is not associated with the people that are married are less have less insomnia. Smoking, not smoking is 0, smoking is 1. So not smoking people have, or smoking people, 1, the high score, would have more insomnia, and people that exercise have less insomnia. And then they looked at a few variables. Asthma was associated with insomnia, depression, well, they just had depression, how much depression they had, and then how much anxiety they had, and those were both strongly associated with insomnia. If you're worrying and you're depressed, that's a very strong indicator or strong predictor of insomnia. Now, what we have done in each of these regression analyses here, they have entered a number of variables into the model. So in this first one, they enter sex, age, education, partnership, smoking, and exercise to see if there's any of the variables that overlap and no longer predict. And sure enough, education, when you put in the other variables, no longer is a significant predictor of insomnia. That's more accounted for by other things here, because perhaps education and smoking might be strongly correlated, and so it's really the smoking that predicts problems with insomnia rather than the education. So here, the demographic models are all put in here, and it explains 6.8% of the variance, and this is significant. Compared to no model at all, the p equals 0.0001. Now, in this first model, the second step, we add the variable asthma impact, and sure enough, that's significant. And the same variables stay significant like they were before. And that explains 8.6% of the variance. That's a change of variance of 1.9%. And that change is also significant. So this is a better model than that one. Step 3, we put in both asthma and depression. And those two are very significant. Now, whether you're living with somebody, that becomes non-significant. And the same thing about exercise. Those no longer are significant predictors either, because they're swallowed up by the depression and the anxiety. And this model predicts 20% of the variation. That's increased, that went up over 11% compared to the previous model, so it's very significant. So this step 3 was just depression. Step 4, they took depression out and put anxiety in, and it pretty much did the same thing. The partnership became non-significant, went up to about 22%. This one's even a little bit better than just depression. The anxiety is a better predictor, so it was significantly significant increase. And so now they put in both depression and anxiety and see how that does. And once again, it increases by 4%, so it's very significant. And then they added some interaction terms in to see if there was some, these are moderator terms. They didn't add anything to it. And let me move this over here. The change in variance wasn't significant there, so the interactions didn't count. But this is how we do hierarchical multiple regression, how we read the table. And one of the key things to remember is that these betas are pretty much interpretable like correlations to see the strength between what we're trying to predict insomnia and the different predictors that we're looking at.